In the previous lesson, we learned how control valves dealing with liquids and gases can be used to control flow, and also learned about choking and cavitation in the valve. Now we're going to look at the proper control valve selection so that we can have this implemented into a process control scheme and have good control. To do this, let's just look at a very simple piping system. I have a system where I have an inlet pressure, which I call P1 of a fluid. It enters a small length of piping with a length of L1, and it comes to a control valve, and the pressure before the control valve we'll label as P2, and downstream of the control valve is P3. The control valve then comes into a pipeline that has a length L2 and then goes through a vertical section of length L3, comes up through an elbow, proceeds to a length L4, and then finally to some pressure P4. And what we want to do is be able to select the proper size control valve and also the piping diameter so that we could have a properly sized system. And we're going to have to understand how pressure drops occur in pipeline systems. This will be a review of your Transport 1 course where you've looked at pressure losses in pipes and fittings, and we'll put this together into one complete package. So in this process, we have, let's say, a known flow rate and some inlet pressure P1 and some known outlet pressure P4. And we want to design the system to handle this. The first thing we want to do is find the total delta P across the system. In this case, P1 minus P4. And we know what those pressures are. And the difference in pressure between P1 and P4 is due to the frictional pressure loss in the pipeline through the straight lengths of pipe and through the elbows. We also have a pressure drop across the valve and also a pressure drop due to the change in the elevation of the pipeline. We'll review some of the Transport 1 course material when we're looking at the pressure loss due to friction in pipelines. And that's equal to the density of the fluid that we have. It also is a function of these K values that we will sum up and the velocity squared over 2. And the sum of the K's is just the K of the pipeline, which we'll talk about in just a minute, but also the K values of all the fittings in the pipe, and we'll see a table that lists these values. For a straight length of pipe, the frictional pressure loss coefficient K can be determined using either the Fanning friction factor or the Darcy friction factor. If we're using the Fanning friction factor, that K value for the pipe is 4 times that factor times the length of the pipe divided by the pipe inside diameter D. If we're using the Darcy friction factor, that K value is just the friction factor F sub D times the length of the pipe divided by the diameter. And as we learned before, the pressure drop across the valve, which in this case is P2 minus P3, and that will be given by the specific gravity of the fluid times the square of the volumetric flow rate divided by the piping geometry factor F sub P and the valve coefficient C sub V, and that's for liquids. And of course, the pressure difference due to an elevation change is just equal to the density of the fluid times the acceleration of gravity G times the elevation change L3. As I mentioned before, we have various types of fittings inside pipelines, and each one has their own respective value of K, which will be included in the pressure loss equation. In our particular case, we have two 90-degree elbows, and in this case, if we use a standard radius, the K value would be 0.75. If we would happen to have other items in our pipeline, say a gate valve fully open, that would have a value of 0.17. Or if we have check valves and other types of valves, we would include those K values also. But in our case, we have two 90-degree elbows, and if we use a standard radius, those values would be 0.75. Now for the pipeline itself, we need to know what the diameter should be, and we calculate the diameter based on recommended typical velocities flowing through the pipeline. Here we see various different types of fluids flowing through different types of pipelines, and we're given recommended velocities going through these pipelines. Gases will typically have a much higher velocity than liquids. In our case, we're dealing with water, and we'll assume that we have a steel pipe. So the recommended velocity of water flowing through a steel pipe is between 0.9 and 2.4 meters per second. So we can use this to help us determine what's the proper diameter of the pipeline. Now I mentioned that we have friction factors for pipelines, and I mentioned that there are two types, a Darcy friction factor and a fanning friction factor. And you need to be careful because they look a lot alike in terms of friction factor charts, but the Darcy friction factor is a factor of 4 times higher than the fanning friction factor. So if we look at our plot in front of us, on the y-axis is the friction factor. In this case, I'm dealing with Darcy, and it's a function of the liquid Reynolds number RC. Okay, and we have a laminar flow region, which is given here on the left-hand side. And in our case, our friction factor chart includes the relationship where the friction factor is just a value of 64 divided by the Reynolds number. Now, for most cases in industry, we often are dealing in the turbulent flow regions, and so we would expect to see friction factors in this region here. If we were looking at to calculate the friction factor, we also need to know what the relative pipe roughness would be. And that relative pipe roughness is the roughness factor, which is the Greek letter eta, divided by the pipe diameter d. So for different types of materials, we have different values of roughness values, and they have units in terms of, in this case, millimeters. And we would divide by the diameter of the pipe, also in millimeters, in order to establish the proper pipe roughness. So we would look at our Reynolds number, we would look at our roughness factor, and then determine what might be the proper value of friction factor. For instance, if our Reynolds number is on the factor of 10 to the 7th, and our pipe roughness is around 0.005, we would find that our friction factor, a Darcy friction factor that is, would be 0.03. If we're using a fanning friction factor chart, and this is typically common in chemical engineering textbooks, it looks almost identical. We have a friction factor F on our Y scale as a function of our Reynolds number and also our pipe roughness. A good way of telling which friction factor chart you have would be looking at the equation in the laminar region. In this case, notice that the friction factor is 16 divided by the Reynolds number, where the Darcy friction factor is 64 divided by the Reynolds number. So if we know what we're working with, we can determine which is the proper equation to use. And so in this case, if we have a Reynolds number of 10 to the 7th and a pipe roughness factor of, say, 0.05, then we have a value of friction factor perhaps somewhere about 0.015. So that would be the two friction factor charts that we have to worry about. Now that we have looked at the friction factors, we notice that they're a function of the Reynolds number and the relative pipe roughness. Both of those require knowing what the inside diameter of the pipe is. In the United States, we have various different types of piping which have different wall thicknesses. And we separate the wall thicknesses by something which we call schedules. For instance, if we look at a 1-inch diameter pipeline, that's a nominal value of the pipe size. But depending on the wall thickness, we would have various different inside diameters. So if I happen to have a Schedule 10 pipeline, the inside diameter is 1.097 inches. If we have thicker walls, perhaps going to a double X value, my inside diameter is now only a little less than 0.6 inches. And the reason why we have different wall thicknesses is due to whether or not we have low or high pressures going into the pipeline. For each nominal pipe size, the outside diameter of the pipe is always the same. It's just the inside diameter changes based on how thick the walls are. And so we have common pipe sizes, and you'll note that once we get past 4 and 4.5 inches, that our pipe sizes then are only on the 5 inches, 6 inches, 8, 12, 14, and then also going up to much larger diameter pipelines, all the way up to 48 inches, we have values for the inside diameter. And these are based on the pipe schedules, which are effectively deal with the thickness. Almost all the time in pipelines, we deal with a Schedule 40 pipe for relatively moderate pressures. And so for less than 10 atmospheres, a Schedule 40 pipe is the common pipeline size that we'll use. And if you remember from the fanning friction factor charts, we need to know what pipe roughness is. And so we have values that we can use. Commercial steel being the most common pipeline material that we use, it has a pipe roughness of 0.046 millimeters. If that pipeline should be heavily rusted, that roughness factor now could be up to 2 millimeters. And you can see quite apparent on you, depending on what type of pipeline you have, you would use a different value of the pipe roughness. So let's take a look at our system that we want to design. We want to use a normal flow rate of 150 gallons per minute of water at 20 degrees Celsius. Now, if we don't have a maximum flow rate, what we'll do is we'll design for about 1.3 times the normal flow rate for our pipeline design. In this case, using that heuristic, we're going to design our pipeline for a maximum flow of 195 gallons per minute. The velocity that our heuristics gives us will be 0.9 to 2.4 meters per second. And so we'll choose 2.4 meters per second at that 195 gallons per minute. Since we'll be working at 150 gallons per minute, our velocity will be significantly less than 2.4. And at 20 degrees C, we need to know the viscosity of our fluid. In this case, it's 1 centipoise, which is equal to 0.001 Pascal seconds. So I need to get my units in a convenient form. So I'm going to calculate my volumetric flow rate. Instead of 195 gallons per minute, I'm going to get it in units of meters cubed per second. So just by doing some conversions, we find that our volumetric flow rate is 0.0123 cubic meters per second. Now I'll use that velocity, that 2.4 meters per second, to calculate the area of my pipe, because the volumetric flow rate divided by the area will give me the, let me rewind, the volumetric flow rate divided by the velocity will give me the area of the pipe. In this case, I take my volumetric flow rate divided by 2.4 meters per second, and then convert meters squared to inches squared. I'll find that my area of the pipe is going to be slightly less than 8 inches squared. And knowing that the area is just pi d squared over 4, I can solve for my pipeline of 3.181 inches. Now, these pipelines don't have an infinite number of diameters. So if I look at my 3-inch diameter pipe and look at schedule 40, I'll find that the inside pipe diameter is 3.068 inches. So we'll select that pipeline for our design. So now I'll use that inside diameter of 3.068 inches and calculate the area of the pipe using standard geometry, and find that the area with that inside diameter is 0.00477 square meters, and our velocity is actually 2.58 meters per second, which is pretty close to that 2.4 meters per second heuristic, slightly higher. However, I'm designing it for a flow rate of 195. My actual flow rate at 150, my velocity will be much lower than 2.58. We have our pipe diameter selected, and we know our velocity. So what we want to do first is let's calculate the downstream value of the pressure from the pipeline. That is P3. First thing we're going to need to know is our Reynolds number, and we can calculate that using the diameter times the velocity times the density of the fluid divided by viscosity, and converting our diameter into meters, our velocity of 2.58 meters per second, density of water 1,000 kilograms per cubic meter, and our viscosity is 0.001 Pascal seconds. We determined that our Reynolds number is slightly higher than 200,000, definitely in the turbulent region for our pipeline. Our relative roughness is the surface roughness of the steel pipe divided by the pipe inside diameter. It's also a unitless quantity, so we convert our units, end up 5.9 times 10 to the minus 4. Using our fanning friction chart, we get a value of 0.00485. The K value of the pipe is 4 times the fanning friction factor times the length of the pipe divided by the diameter. Well, the total length of my pipe is L2 plus L3 plus L1, which is a total of 21 meters of pipeline. Using our diameter and converting that into inches, we find that our K value for the pipe is 5.2. The fittings, all we have in our pipeline downstream of the control valve, are just 2 elbows. And so each elbow has a K value of 0.75. So our K value of our fittings is 1.5. So our total value for the pressure loss due to friction is rho times the sum of all my K's times the velocity squared over 2. And we plug in our numbers using the 2.58 meters per second as our velocity. And then converting units, we find that our pressure loss due to friction is 3.25 pounds per square inch. There's an elevation change also we have to account for. So P3 will be equal to the delta P elevation plus the delta P friction plus that outlet pressure P4, which I've already converted into PSI. So using the density of the fluid, 1,000 kilograms per cubic meter, 9.8 meters per second squared, a 10-meter elevation change, and converting our units to PSI, adding to it the frictional losses plus the outlet pressure, our value of P3 is 32.2 PSI. Without going into detail, I can calculate what P2 is, which is just P1, in this case we have it 5 atmospheres, minus the frictional pressure loss over the pipeline having a length of 5 meters. And doing that calculation, we find that P2 is 72.9 PSI. And then taking the pressure difference, we find that across the valve, this is P2 minus P3, we have 40 PSI pressure loss across the valve. A heuristic for control valve is that the pressure drop across the control valve should be at least 10 PSI or half of the frictional pressure loss, whichever is largest. Well, our frictional pressure loss is only 3.25 PSI. So by having a pressure drop across the valve of 40.7 PSI, we know that we should be able to have good control across this valve. Now we want to select the proper control valve. And using our control valve equation, we know that C sub V will be equal to our volumetric flow rate in units of gallons per minute divided by the piping geometry factor F sub P divided by the square root of our pressure drop across the valve in units of PSI divided by the specific gravity of the fluid. Let's look at that piping geometry factor F sub P. It's a function of the valve coefficient squared times the sum K when we're dealing with inlet and reducers and outlet reducers. We have to determine the piping geometry factor. And it's also a function of the throat diameter in the valve, which is called D. Now, we don't know CV yet, so we can't calculate FP, and we can't calculate FP unless we know CV. And so what we're going to do is first make an estimate of what our value of D is. And typically, we often choose a valve size that is approximately one pipe size smaller than our line size. Well, our line size is 3 inches, so we will first look at a 2-inch valve. Now, in the lower right-hand corner, I have values of 2-inch valves, but I don't know which one I would select because I don't know what CV value I have. So the first thing I'm going to do is just make an estimate. I'm going to say that my valve diameter, the throat diameter, is 2 inches. This way I can calculate what my values of K1, K2, KB1, and KB2 are using those values. The pipeline upstream is 3.068 inches, and same as downstream. So using just a simple value of 2, I calculate my K1 is 0.165, my K2 is 0.331, KB1 0.819, KB2 of 0.819 also. So I'm going to assume that I have an FP of 1 for the time being. And so what I want to do is calculate what that estimated value of CV is. So my flow rate is 195 gallons per minute. Let's first assume a FP of 1.0. and square root of the pressure drop. And that gives me a CV value of 30.6. If I look at my 2-inch valves, only the very last one will give me a value of 30.6 because all the others are much too small. So I would have an orifice diameter, in this case, of 1.625 inches. Now that I know my estimated value of CV, 30.6, and my true diameter, 1.625, I can recalculate my K1, K2, KB1, KB2, and I can recalculate my value of FP using that first estimate of CV, and it turns out to be 0.8. By using the value of 0.8, I recalculate my CV, and now it's at a value of 32.8. Again, 1.625 inches is still appropriate. I'll recalculate FP using that new CV value and end up at 0.94. And then recalculate the CV again at 32.5. And that's as far number of iterations as I want to go. So I'm confident that that 2-inch valve with a 1.625 inch orifice diameter will definitely allow me to control the flow at 195 gallons per minute. In this case, it's the valve opening under that condition is going to be somewhere between 70% and 80% opening at that maximum flow. Here we're looking at a plot in which I varied the flow rate using that linear control valve that we just selected before. And I changed the flow rate in the pipeline, varied it from 0 to a maximum of about 200 gallons per minute. And what I did was, first I calculated the CV across the valve as a function of flow rate. So at the highest possible flow rate, 200 gallons per minute, I calculated the CV that I need for my valve, and it's around 34. At 100 gallons per minute, the CV value is about around 17 or 18. At 0 gallons per minute, the CV for the valve must be 0. So the orange line is the calculated CV for my valve based on the calculated pressure drops as a function of the flow rate. In this whole system, I didn't change the diameter of the pipe at all, left it at 3.068 inches. On this plot, I also included the CV for that 2-inch valve with a 1.625 inch orifice, and I plotted its value of CV as a function of valve opening. So at 100% valve opening, the CV for that valve is 46. At approximately CV value of 25, we see that it would be at about 60% opening, and down, say, at around a CV value of 10, we're somewhere below 20% opening. So on the right-hand y-axis, I have the valve opening percentage as a function of the valve CV. And on the left-hand y-axis, I have the calculated CV as a function of flow rate. And I want you to take a look at both of these two particular lines. Okay, we chose a linear valve for starters. And notice that the valve opening is a linear function of the CV that you get for that valve. On my system curve, the orange line, the flow rate is essentially linear with the calculated CV I got from all my equations. And trying to do a good selection of what valve we should choose, we want to pick one where the valve opening versus CV is similar to the flow rate versus CV in terms of whether it's linear or curved. In this case, both of them are linear. A linear valve is defined by that. So you would expect a linear valve to have a CV and valve opening percentage being linear. And my system is linear. My flow rate is linear with CV as well. This means that this valve would be a good selection for this system. Now we're going to take a look at modifying our system. Instead of L4 being just 1 meter long, I'm going to change it to 100 meters. And now my curves are slightly different. I have a longer pipeline. It went from 21 meters to 140 meters long. And the orange line is my system curve, meaning the calculated CV using friction factors and everything. Notice what's starting to happen. We start seeing some curvature of this system line of flow rate versus the calculated CV. So it's beginning to curve. I also plotted that same value of CV and valve percent opening just like before. But now I have a little bit more curvature to my system line. And I want to have a valve that has a similar curvature to it. We can look at a different style of valve, in this case an equal percentage valve. Okay, so from my Mason-Nealon catalog, I also found equal percentage. And I chose a 2-inch valve with a 1.625 orifice diameter, and it had a maximum CV of 46 at 100% opening. And now I'm just going to plot the value of percent of plug travel as a function of CV on the next curve. My system curve remains the same. That's my calculated CV and for different values of the flow rate. But look at the equal percentage curve, which is in blue. You can see that it has some curvature to it. And so, although my value for the system curve shows some curvature, it doesn't show anything nearly as intense as an equal percentage valve does. If we go back to the previous slide where we plotted the linear valve, you would notice that that linear valve is more closer to my system curve than the equal percentage. You will see some cases where if we have large frictional losses in pipelines, especially if we have things like heat exchangers in the pipeline, filters and the like, or lots of fittings or long pipelines, we will find that our system curve, which I display in orange, will start to match the equal percentage valve curve, which is displayed in blue. And in those circumstances, we would select an equal percentage valve to control the flow rather than a linear valve. So this is how you decide between which type of valve you want, a linear valve or equal percentage. You want to look at your system curve and then compare it to the valve curve and see which one gives you a better match. That concludes this lecture for this week.